Okay, so we looked at last week about the motion estimation, okay? And so if you remember, what we did was looked at exhaustive or full search block matching, okay? So the idea was if you have a block in an image, we want to find what the most similar block, in the next frame. So first I'd like to point out one practical aspect, okay? What do you think is the effect of the block size? Okay, so if you have a block size of, if your block that you're considering is a size 1 by 1, so you're just looking at one pixel, what is the advantage and what is the drawback? Okay, so I can tell you the advantage. The advantage, you have one vector per pixel, which is good. What is the problem with having a block size of 1 by 1 in block matching? There's a big problem with it, okay? Yeah? Go ahead. Processing time, yes, will be increased.
You're only going to match one tiny little thing to one tiny little thing, and it could just be...
Exactly, right? So the question you have, like if you look at a 1 by 1 block, how many different blocks you will find? All right? You'll find if you have 256 different values of intensity, then you have 256 possibilities of blocks. So if your pixel is, say, white, you probably will find loads of pixels that are white as well. Okay, so you probably have a few other thousands of pixels that have exactly the same appearance. Right? If you take a big block, the advantage is that you will make sure that your block contains something unique about it, and that will be easier to match in the data frame. The problem, of course, the resolution will drop, and maybe if you have a rotation or anything like that, then matching this big block and expecting that none of the pixels have moved in between is a bit, of a stretch. So the block size definitely is something very important, and I would say it's, however we looked at any kind of modern motion estimation technique, optical flow technique, there will be a parameter that will be related to the block size, okay? That will tell you what the scale of the local area is of consideration. All right, so we looked at the technique that is used in compression, which is block matching. There is this alternative technique that is more kind of at the heart of what people would say optical flow. But I mean, as I said, it's the same as motion estimation, really. So we'll leave it there, okay? So here we're trying to work with the gradient of the picture to have a better prediction, okay? So right now, to be able to find, one of the big problems we have to try every single possible candidate position, and it's very extensive. So maybe there are quick ways of trying to find, to at least give us a better educated guess at where to look for, okay? So let's start from the beginning. We have the equation looks like something like that. Okay, so you have the picture at frame n at some location x. So when I write the x this way, really what I mean is small x and y. Okay, so we're looking at the pixel coordinates x and y. So I use kind of vector notations if you want. So this pixel intensity, I say, is the same as the pixel intensity we have in the previous frame, but we have some displacements, okay? I'll put an underscore just to make sure that we realize that we're talking here about vectors, okay? So that's kind of the general equation, and we say, well, you need to add some noise to some extent, so, something like that here, okay? So that's the equation we have. Now, when we do block matching, what we say really is we say that within a block, the vector here would be the same, okay? So a priori we have, this displacement will change from pixel to pixel, and that's the whole point of the exercise. But when you do block matching, you kind of assume that within some region, that displacement would be very small. So if we're trying to look at that in terms of what we're trying to minimize, or in terms of loss function, what you would have is a term like this. So you have a function of, say, the position and the displacements. And if using the mean square error, you would have something like that. So you have a sum over all the pixels over your blocks. Let's call it B, okay. Right. Pixels of all your block of interest of the difference between your actual pixel and the predicted position. Okay, so that again. So, all right, this is probably not the correct way of doing that. Sorry, notations are not very good here. I'll index here. All right. So what I'm saying here is that I have a block around the pixel location X, and I'm looking at all the pixels locations within that block, and I test whether that's true or not. Okay, so I just have this squared error that I'm trying to minimize. Okay, and what we're trying to find is, we're trying to find the argmin of that particular function. Okay, so we're trying to find the motion vector that will minimize this error. That's kind of what we're trying to do. Okay, so it's just formalizing that in terms of maths, what we've seen before. The only thing that I specify that is important for the rest is the fact I'm using the square differences between the pixels. Okay, so we've seen in block matching, usually more use something like the absolute difference. So here I'm just going to look at the square difference. Okay, so where is the problem with that? Okay, so the problem you have to resolve that directly, be like, okay, so we have a mathematical expression, we express that, and we want to minimize that. What stops us from finding D directly? So what stops us is that D is it's buried. It's very nonlinear. Okay, so D is inside. It's a position inside the actual picture. It's here. Okay, so it's not obvious that you have one level of indirection here. So it's a function of D, and you take the square difference between that, and you don't know about that too much. Okay, so that's where it's complicated, because you don't know this function too much. The last frame at location X plus D, but that could be anything. Okay? You don't have any closed form expression for that. But what we can do is try to solve the problem to say, right, what if the displacement is very small? Okay, so you say that I imagine that my displacement is a tiny vector. Okay, in this case you can use Taylor expansion. Okay, so if you use Taylor, your Taylor series, then so this is a trick. Okay, is to say the last frame. So this expression here. If you look at, so this is too hard to really work with, but maybe I'd say this is roughly, if D is sufficiently small, you have this Taylor expansion you can use, okay? And so it's in 2D, okay? So you have, it's a gradient operation. And I'm going to index that by dx, okay? So just Okay, so remember D is a vector, and so you have these strange notations. But basically what I'm saying here is that the intensity at pixel coordinate xc plus d, if d is sufficiently small, I say, well, that's the same at pixel location xi. And I add a bit in both directions, and this is the variation of the picture along the direction x, and this is the variation, the rate of change, if you want, in direction y. Okay, so look at the two rates of change, both in the horizontal and vertical direction, and you say that a small difference in small change in dx and in the horizontal, where you combine the rate of change and the actual amount of change you bring, okay, for both directions. All right, so that's just simply Taylor expansion in 2D. So what is interesting with that? Okay, so let's. So what is interesting with that is like this is linearization. Okay, so you have a nonlinear problem here, which is this function of d, and now you have something linear because now these guys are you can be pre-computed. Okay. So you can pre-compute these two parts. They're constant, okay? It's just the gradient in the x and y of your picture. And then you're left with this simple expression which relates your shift in x and y with respect to that, okay? So that's interesting. So it means now that you have a simple linear expression. And this expression has a name. It's called the optical flow equation, or the flow constancy, but there's different names for that. Yes? So here imagine that almost nothing has changed in your picture. There's almost no motion. Okay? Now the argument will go the same. Basically, I'm trying to work out to say, right, we can't solve the problem if d is any number. I'm trying to restrict myself to the case where d is very small, okay, so minuscule motion. And then I say, right, we can actually do it. You know, we'll show that we actually can resolve the problem when d is small. Then we'll say we have a closed form solution for that, and we'll be able to say, to iterate, to say, well, if, you know, like a Gauss, like a Newton search, you know, you're able to say, right, let's assume that we're close to the solution. Let's try to find what d is and give that as an update. Let's go in that direction, and then let's try to solve that. Does that make sense? It becomes clearer afterwards, maybe. Okay, so basically, if I rework my equations here, now my energy or my loss function is this sum of squared over my block of the pixel value at a particular pixel within that block and this predicted value you have, okay? All right. This is actually least square, okay? Because here it's a linear model, okay? So this, and this are just scalar numbers. They're just your coefficients that you can pre-compute. And dx and dy are the coefficients you're looking for. And so you have here a linear equation, and you're looking at the, you know, as trying to find the minimum of that square. Okay, this is least square, and we know how to solve that. Right? So I'm just going to show you that. In a second. So another way of looking into it is to say, if I look at all the pixel locations I have, I'll put that on the other side. And then you do that on both sides. So basically, on the left-hand side, you have the difference between your, it's a displaced frame difference with no motion, okay? So just look at the, how things are changed. And here on the right-hand side, you have how you could predict that by just looking at the local gradient and seeing if the gradient is going in this way. I mean, it's Taylor, okay? So basically, the idea is to say if my pixel here is dark, but in the other picture it's bright, then I look locally, if I go left or right, then I will get darker or brighter, and I say, well, I want to go in the direction which is brighter to match the other picture, okay? So anyway, so you have that. The simplest way to go about solving that is to go through matrix notation. So you have I say a big matrix called G, which will contain all the gradient in X, and then all the gradient in Y. Sorry. And then you have here the difference. So you say something like JD, GD is equals to something like that, okay? Something that tells you the difference between that. And then you say, well, the best estimate I have for D would be G transpose G minus 1 G transpose of. Okay, so this is a vector, okay? So this is a vector that contains all the difference between all the pixels within that block, okay? All right, so you have a simple way of going about that. And so it's pretty cool because then you know if your displacement is quite small, then you can actually, you don't have to do the block matching, you don't have to try all possible solutions. You end up with a simple operation. So this is a 2x2 matrix, and this is a 2x1 matrix, 2x1 vector at the end. And so, you know, the G matrix only contains information about the gradient of the picture, so you don't have to re-estimate that. That is done, and all that is just there. Okay? Yes?
Is this really susceptible to noise? Keep thinking noise is motion.
Yeah, so noise, okay, so interesting question. So how does noise interfere in that? So if you have noise, that means that your G matrix, here you have something plus noise and something plus noise in Y, okay? And so really when you do the G transpose G matrix, what you get here is the same term you had before plus something like that. So really what you're doing here is the noise you're adding adds up. This is usually 0 because this is uncorrelated. So really what you're doing is in presence of noise, G transpose G becomes G transpose G plus some kind of a diagonal matrix with epsilons on the side, okay? Which is not a big deal, it's not a major problem. It just basically damps the estimate of your D. Okay, so noise is an issue, but it's a well-behaved issue. Okay, it's not a bad thing. Is it okay? Yeah. So I'll just write down the equation here exactly for what G transpose G, because this is the matrix you have to inverse. Okay, and so let's put more space. So basically, what we're looking here at is something like that. At all. But it's the same term, okay. Sorry. Okay, so it's a 2 by 2 matrix. On the diagonal, you have the sum of the squared gradient in x and y, and then you have the cross derivative terms here. So let's look at the problems you might have. Okay, so this is a quite important metric that is being used a lot in tracking and so on. So basically, in this example, you look at what could be the problem. And if the matrix is not invertible, that basically means that one of the eigenvectors, or one of the eigenvalues is null. Okay, so there's 3 different cases, either where the matrix is null, okay, so both eigenvalues are 0, and that can happen if you're, so when would that happen? Okay, so when would both eigenvalues be 0? Okay, can somebody have an idea of what? So, I mean, when would that matrix not be invertible? Do you have? So it would happen because the gradient is null everywhere. Okay, so both the gradient in x and y would be null. Okay, and so then you have 0, 0, 0, 0 everywhere. Okay, and that happens quite frequently in a picture. That's when you have no texture. Okay, so you're looking at a wall. There is no texture. There's no gradient besides for noise, and therefore, because you're looking at the gradient here, there is nothing. That is, everything is 0 basically, and therefore this becomes 0, and you can't invert that. Okay, it's nothing new here. Okay, we know if there is no texture, even with full block matching, full search block matching, if you move a bit, there'll still be no texture, be the same information. So therefore, you can't tell where the block is. Okay, and it's called the aperture effect. Okay, so. Quite an important term here. So the aperture problem, the aperture problem is that if you have nothing to lock on, you cannot find motion. Okay, there's too many possibilities. And though this is given by the case here, you have 0, 0, all the both eigenvectors are 0. The second problem might be, okay, you might not be able to invert that if just one of the eigenvalues is 0. Okay, and if one of the eigenvalues is 0, I'll help you there. But that basically means you're at an edge. Okay, so when you're at an edge, the gradient goes only one way. Okay, so all the gradient goes just in one direction. And that means that when you work out when you do the maths here, it's not that complicated. But basically here, one of the you're missing information. You only have information in one direction, not in the other direction, and therefore you cannot invert that matrix as well. Okay. The only time when you can invert that matrix is when you can measure gradient in 2 different directions. And that happens at corners. Okay, so when you're at a corner, okay, so if you have So this is a picture, and this is the corner of your picture. At this corner, you have gradient going in both directions. Okay, so locally, the gradient, has a response in both directions, and therefore, in this case, you would have this matrix will have two eigenvectors, the two eigenvalues that are non-negative, and therefore you can invert that stuff. Okay. So this kind of analytical analysis, okay, is very much the same as with full block. Like there's nothing new from block matching as we've seen it, brute force. We're not resolving things that we can't resolve. It just says, if you're at a corner, then we can resolve that and we can give you a precise indication of the direction for a small displacement. All right? But if you're just at an edge, you cannot resolve, or you can only resolve in one direction, you cannot resolve in the other one. And if you don't have an edge, if you just have a blank piece of, a flat region, then there's nothing you can do. Right? So that's kind of the same. We don't resolve more maths, okay? This is the same problem. So that's for small displacement. So the question is, how do we go further than small displacement? So two strategies that are combined usually. So the first one is to iterate. Okay, you first assume there's no displacement, go there, estimate what the D is, find that and apply it, and then shift your picture a bit and then resolve again. Okay, so you keep on iterating, you move a bit forward. The other approach is to come back with what we showed last week, which is multi-resolution. So what's the definition of a small displacement? Okay, well here, because looking at a pixel, we're looking for a displacement D which is smaller than a pixel. Okay, so we're looking for 0.5 pixels or so. 0.5 pixels at a full res, it's not much, but if you start to look at level 4, already that's a few pixels here and there. Okay, so that assumption that displacement is small could still work, but at a different resolution. Okay, so if you look at a very low res image, then 0.5 pixels is actually quite a lot of pixels at the higher res. Okay, so you can work your way this way. So you use that at low res, update it at higher res. And most motion estimation techniques kind of are based more or less on these principal ideas and working at different resolutions. So there'll be a lab tomorrow, and you'll be working on not on that specific one, so you'll be working on the full block matching. You will see some of these aspects, okay? You need to realize, okay, when is motion estimation failing or not? You'll feel like, okay, if you have a flat region, it'd be hard to get anything good. You'll be looking at the block size, okay? So the bigger the block, the more certain you are to be able to invert that matrix. So you'll find directions, but maybe that information won't be very accurate, so you have to you'll find a trade-off and so on that. Okay? That's pretty much it. So this will be in the slides. So yeah, more examples of the aperture problem. Yeah, if you look here, you can see it's all about locality, okay? So you have the square, your object is a square, it has moved a bit. But if you look locally, if you just look at your block, if you're at an edge, all you see is that something has moved, that the vertical line here, the boundary has moved from here to here, right? But you don't know whether it's going up, down, or straight, okay? You just don't know that. You don't have enough information, okay? So you only solve part of the problem. You know it has moved at least along the x direction, but you don't know by how much on the y direction. So good motion estimator, basically what they do is they try to propagate information for where you know, okay? So they will look at, they can work on a pixel basis, but they will say, if you have ambiguity, reuse information from the nearby pixels to kind of guide you at a particular location, right? But it's actually a very tricky business and still many unsolved problem, okay? So something to keep in mind here, interesting, okay, I'll say that again. You can already do good stuff, good work at corners, okay? And so therefore there's a huge amount of work done on detecting corners or corners that are very good at, for tracking, very robust to all sorts of noise and so on. And usually you have two ways of going about things, okay? So either you track every single pixel, in which case you need to have these kind of motion estimation techniques that will, try to infer or propagate the information at every single pixel, or you try to throw away all that and say all I need to know, what you need to know about is roughly for a few pixels in the picture where they go to. In which case, what you do is you select the best one. You look at the corners and you say, right, these are corners. I know I have reliable information on those, and I'm just trying to track those. Okay. So for most applications, this is what you do. You just pick up the corners. You might have very few corners. Okay, in a picture, you might only have 100 corners, 20 corners, okay? Maybe very small. But anyway, you look at these corners, you track them, and you do something with that, okay? Even that part can be tricky because corners can change in nature and can disappear and all sorts of problems. So yeah, so this is another example of that. I think you have an example like that actually in your system where you can see the vectors, and you can see the vectors are only correct at the corners, but in between on the lines, they just don't make any sense. And that's because they could indeed match to any of these locations. The appearance is the same. To finish, okay? So motion estimation it's particularly hard. So aperture problem is one big problem. The other problems are listed here. So the first one is fast motion, okay? So, and that is because of the computational issues we talked about. Usually you limit the scale of the motion. You say the motion will be within some distance, some search window, say plus or minus 10 pixels, okay? But sometimes really objects move fast. Okay, and then if they move too fast, then you fail to detect that. And that is usually quite a big problem. Second problem is occlusions. Okay, so occlusions, we didn't talk about that here, but basically all the equations I wrote are totally incorrect for occlusions. Okay, so there's no good model for occlusions that we have. Okay, so it's always a trade-off. But basically, we set as occlusions pixels that we find hard to match to anything else in the other frame. And we say, well, probably then it was occluded. Okay? Then you have transparency and reflection. Basically, if you have two layers, one goes this way and the other one goes this way, it means that a pixel actually goes both ways. If you look at a particular pixel location, you have two objects at that particular depends on which layer you're looking at, if it's a foreground or background layer. So the foreground layer might go one direction and the background layer the other direction. So per pixel, you really should have two motion vectors. And obviously, in the way we're dealing with that here, we just assume that the motion is the same within some block. But then it doesn't take into account the fact that maybe there exists two motions going on. Okay, so most motion estimations, motion estimation algorithms will totally break down in case of transparency or reflection. And then you have all the crazy non-rigid objects that exist in real life. Okay, so hair, for instance. So all these particles and all this kind of stuff. And you finish with motion blur, which means like everything is blurred and you don't have any corners. The motion went too fast, and basically you don't know where to match against what. Okay. It's good to know that all these exist, okay, and to have a pretty good idea of what's going on, and it's kind of a healthy reminder that definitely with motion estimation, when you run it, your expectation should be that it doesn't work everywhere, Okay, so when you have to use motion estimation, okay, first you will slow down your process by quite a lot. And then you need, when you design an application, you need to say, okay, how do I handle failure? And that's because failure will happen for 20% of the blocks. Okay, so 10%, 20% of the blocks will have issues of, they're actually occluded, or there's too fast motion, or it's just hair and you don't know what to do for hair, and all this kind of stuff, okay? So the model we have for motion, it seems like a reasonable model, but in fact it only covers something very incomplete, and it's just be prepared mentally, okay, this is not going to work, so when it doesn't work, how do we detect that? So one of the big problems in application is to account for that, detect for errors in the motion estimation, and trying to find a fallback solution for that. All right, that's it.